you're looking at a galaxy. Odds are, in your head, it's a spiral. Flat disk, sweeping arms, the whole cosmic pinwheel thing. And honestly, fair enough. Spirals are kind of the poster child of the galaxy world, but here's the thing. That pretty shape is hiding one of the cleanest physical laws in all of astronomy. Spiral galaxies look like someone spun a cosmic frisbee and let gravity do the decorating. You've got a flat disk, a bright center, and those iconic arms swirling outward. But what makes spirals genuinely wild isn't how they look, it's how predictable they are. Here's the deal, if you measure how fast a spiral galaxy is rotating, you can figure out its total mass. Not roughly, not in the ballpark, like precisely. The faster it spins, the more massive it is. That's called the Tully-Fisher relation, and it's one of the tightest empirical scaling laws in extragalactic astronomy. Rotation speed alone tells you total mass. Physicists love when the universe is this cooperative, but it gets better. The shape of a spiral's arms actually tells you how much gas it has left. Tightly wound arms, like in Say-type spirals, mean about 4% gas relative to total mass. Loose, floppy arms, like SD spirals, hold up to 25%, so you can literally look at a spiral and estimate how much raw star-forming fuel is still inside. That's not a rough guess. That's the galaxy wearing its resume on its sleeve. And these proportions aren't just a local thing. The relationship between a spiral's size and its mass follows a consistent scaling that holds from nearby galaxies all the way out to spirals observed just 2 billion years after the Big Bang. These structures have been geometrically self-consistent across most of cosmic history. So spirals aren't just pretty, they're one of the most predictable, well-behaved objects in the universe. Which is great because from here, we're scaling up. Individual galaxy types, galaxy groups, clusters, and eventually the largest structures in the observable universe. Let's keep going. Barred spiral galaxies. So you know those nice, clean spiral galaxies we just talked about? Most of them have a giant bar of stars cutting straight through the middle. Not some of them, most of them. About 65% of spiral galaxies in our local universe have this rigid, straight structure slicing through their center like someone shoved a beam through a pinwheel. The Milky Way almost certainly has one. You live in a barred spiral. Congratulations. Now here's where it gets interesting. That 65% number, it wasn't always that high. When we look at galaxies in the distant past, only about 20% of spirals had bars. So bars have been steadily showing up over cosmic time, like a trend that caught on. The universe started with mostly clean spirals, and then slowly, more and more of them grew these central structures. Bars are, cosmically speaking, kind of a recent fashion statement, and for a long time, that made sense. The assumption was that bars form slowly through internal gravitational instabilities, meaning galaxy needs to be mature and settled before a bar can develop. Reasonable, right? Yeah, well, JWST blew that up. Astronomers have now directly observed well-formed bars in galaxies as they existed 11.5 billion years ago. That's barely 2 billion years after the Big Bang. Two galaxies in particular, Cosmos 74706 and Sears 2112, both show clear bars at a time when the universe was basically a toddler. That completely overturns the idea that bars need billions of years of quiet evolution to form. How they got there so early is honestly still an open question. But bars aren't just decorative. They actively reshape their galaxies by funneling molecular gas inward toward the center on scales of a few hundred parsecs. That gas can feed intense bursts of star formation near the nucleus, or it can feed the supermassive black hole lurking there. Bars are engines of redistribution, rearranging a galaxy's guts from the inside out. So bars are common, they're surprisingly ancient, and they're actively doing stuff. But what happens when a galaxy stops doing stuff entirely? Elliptical galaxies. Ellipticals get a bad rap. People look at them and see a smooth, featureless blob of old stars. No spiral arms, no dramatic dust lanes, no flare, just a big glowing egg sitting there. Boring, right? Not even close. Ellipticals are the heavyweights of the galaxy world. Nearly every galaxy above about 100 billion solar masses is either an elliptical or its close cousin, the lenticular. Spirals basically don't exist at that mass scale. The biggest, most massive galaxies in the observable universe have almost universally shed any disk structure they might have once had. So calling them boring is like calling a heavyweight champion boring because he doesn't do backflips. And here's what makes them genuinely beautiful to astronomers. You can take three properties of an elliptical, its stellar mass, its physical size, and how fast the stars inside it are buzzing around, and compress all three into one tight empirical relationship. That's called the fundamental plane, It's a scaling law that lets you trace an elliptical's entire formation history from just a few measurements, 3 dimensions of complexity collapsed into one clean surface. But the real clue that something weird is going on comes from the size-mass relationship. Small ellipticals barely grow in size as they gain mass. The scaling goes roughly as radius proportional to mass to the power of 0.13, basically flat. But once you cross into the giant elliptical regime, that scaling jumps to mass to the power of 0.68. These things balloon in size. That structural break tells us that small and giant ellipticals were probably assembled through fundamentally different processes. Small ones may have formed through early gas collapse. Giants, likely built up through mergers, possibly many of them, stacking galaxies on top of galaxies over billions of years. So how do galaxies lose their spiral structure and end up as these massive smooth objects? Well, there might be a middle stage, lenticular galaxies. Okay, so we've got spirals with their arms and gas and star formation, and we've got ellipticals sitting there like retired footballs doing absolutely nothing. Lenticular galaxies are what happens when you can't pick a side. They're classified as S0, and they're basically the galaxy equivalent of an identity crisis. They have a disk, like a spiral. They have a bulge, like an elliptical. But they have almost no spiral arms, almost no gas, and almost no new stars being born. They look like someone took a spiral galaxy and just turned it off. And the numbers back this up. When astronomers point radio telescopes at galaxies to look for neutral hydrogen, which is the raw fuel you need to make stars, about 89% of blue spiral galaxies show up. For lenticulars, 15.6%. That's it. Almost completely drained. Whatever gas these galaxies once had, it's gone. And it's not like star formation is hiding in a few corners. Surveys using integral field spectroscopy show that only about 5% of the regions inside a typical lenticular are actively forming stars. The whole disk has basically shut down. So the obvious question is, what happened? Are these just spirals that ran out of gas? Maybe. Some lenticulars sit in dense galaxy clusters where the surrounding environment can strip gas away, like a cosmic pressure wash. Others might have slowly exhausted their supply internally, a process called strangulation, which is a pretty metal name for something so boring. And some might have formed through minor mergers, smaller galaxies crashing together and scrambling the structure just enough to kill the arms but keep the disk. The honest answer? Probably all of the above, depending on the galaxy. Lenticulars are a frustratingly mixed bag, and astronomers are still sorting through it, so lenticulars are stuck in the middle. But what about galaxies that threw out the rulebook entirely? Irregular galaxies. Every classification system has a junk drawer, a category that basically means doesn't fit anywhere else. In galaxy taxonomy, that's irregulars. No clean disk, no spiral arms, no elliptical symmetry, just a blob. Sometimes a lumpy blob, sometimes a stretched out blob, always a blob. But here's the thing, these aren't failed galaxies. They're not broken spirals or ellipticals that gave up halfway through. Most irregulars are gas rich and actively forming stars, sometimes vigorously. They just do it without any structural discipline whatsoever. They make up roughly 3% of galaxies in the local universe, with diameters typically spanning 1 to 10 kiloparsecs and stellar masses ranging from about 100 million to 10 billion solar masses. Small, but busy. The most famous examples are basically in our backyard. The Large Magellanic Cloud sits about 50 kiloparsecs away, spanning roughly 10 kiloparsecs across. The Small Magellanic Cloud is a bit smaller at about 5.8 kiloparsecs. Both are satellite galaxies of the Milky Way, visible to the naked eye from the southern hemisphere, and both are visibly distorted by tidal interaction with our galaxy, which is exactly the kind of gravitational interference that creates irregulars in the first place. Get too close to something massive, and your structure gets pulled apart like taffy. And despite being classified as chaotic outliers, irregulars dominate the low-mass end of the galaxy population. They're key laboratories for understanding star formation and chemical enrichment at small scales. Their star formation rates span several orders of magnitude, which means some are barely ticking along while others are punching well above their weight. In other words, the junk drawer is full of power tools. You just have to open it. So what happens when you shrink things down even further? Dwarf galaxies. So we've talked about galaxies that are big, bright, and easy to spot. Now let's talk about the ones that aren't. Dwarf galaxies are small. Stellar masses range from about 1 million to roughly 1.5 billion solar masses. Some are so faint they're barely there. But here's the thing. They are the most common type of galaxy in the universe. Over 400 have been cataloged just in our local cosmic neighborhood, with distances pinned down down to about 5% precision using Hubble. And the count keeps climbing every time we point better telescopes at darker patches of sky. So why don't we hear about them more? Because many of them are almost invisible. Take the dwarf galaxy caught lensing a background source in a system called B 1938 plus 666. Astronomers measured its mass at around 190 million solar masses. Sounds reasonable. But its mass to light ratio was at least 3.5 times what you'd expect from stars alone, meaning most of that galaxy isn't stars, it's dark matter. You're looking at a gravitational structure held together by stuff we can't see, with just a sprinkling of stars on top like sad confetti, and it gets weirder. An entire class of galaxy ultra-faint dwarfs wasn't even identified until around 2005. Before that, they were just too dim for our surveys to pick up. An entire population of galaxies hiding in plain darkness, which raises an uncomfortable question: how many more are out there below our current detection limits? We literally don't know. Dwarf galaxies also sit at the center of one of cosmology's biggest unresolved fights. These tiny systems lose their gas somehow, but nobody agrees on why. Is it supernova feedback blowing the gas out from within, or does the surrounding environment strip it away? The answer matters because it directly affects how we model dark matter behavior at the smallest scales. The most numerous galaxies in the universe, and we're still arguing about how they work. So what happens when galaxies stop just sitting there and start doing something dramatic? Starburst, galaxies. So some galaxies just don't know when to stop. Starburst galaxies make up about 1% of star-forming galaxies in the local universe, 1%. But that tiny sliver is responsible for roughly 3 to 6% of all the star formation happening right now. That's like one kid in a class of 100 eating 6% of all the pizza. You notice that kid don't? The poster child here is M82, the cigar galaxy about 12 million light years away. The Milky Way forms roughly 3 solar masses of new stars per year. That's our whole galaxy, all 100,000 light years of it, cranking out about 3 suns worth of material annually. M82's central region alone is doing about 30 solar masses per year, 10 times our entire galaxy's output, squeezed into a core region a fraction of the size. It's like comparing a campfire to a blast furnace, except the blast furnace is also on fire. An M82 is considered moderate. In the most extreme starburst events, star formation rates can blow past 100 solar masses per year. At that pace, a gas reservoir that took billions of years to accumulate gets burned through in as little as 100 million years. Billions of years of fuel gone in a cosmic eye blink. That's not sustainable. That's a galaxy running a sprint with no finish line. But here's the thing. Most of these starbursts don't just happen on their own. The majority of local starbursts are triggered by mergers or close gravitational interactions between galaxies. Two galaxies get too close, their gas gets compressed and shocked, and suddenly the star formation dial gets cranked to maximum. It's a violent phase, not a quiet internal decision. And once it's over, the galaxy that comes out the other side is often fundamentally different from what went in. Less gas, more stars, sometimes a completely new morphology. So starbursts aren't really a type of galaxy. They're more like a phase, a fever, and sometimes the fever changes everything. Speaking of galaxies behaving strangely, let's talk about what happens when the center of a galaxy gets really, really bright. Active galaxies. So most galaxies just sit there, doing their thing, stars orbiting, gas swirling, nothing too dramatic, but about 10% of known galaxies have something extra going on. Their centers are absurdly bright. Not just, oh, that's a nice nucleus bright. We're talking a central region so luminous it can outshine every single star in the entire galaxy combined. Billions of stars, and this one tiny patch in the middle says, hold my beer. That excess brightness comes from matter spiraling into a supermassive black hole at the galaxy's core. As gas and dust fall inward, they form a swirling disk that heats up to insane temperatures and blasts energy across the entire electromagnetic spectrum. Optical, ultraviolet, X-ray, radio, all of it. That's called an active galactic nucleus, or AGN, and the galaxy hosting it is an active galaxy. Now here's the satisfying part. You've probably heard a bunch of different names thrown around. Seyfert galaxies, quasars, blazars, radio galaxies. Sounds like a whole zoo of exotic creatures. But they're all the same fundamental thing, a supermassive black hole eating material. The different names mostly come down to how bright the feeding is, whether the black hole is launching jets of material at nearly the speed of light, and the angle you happen to be looking at it from. Stare down the barrel of a relativistic jet, that's a blazar. See the whole system from the side with big radio lobes? Radio galaxy. Same monster, different seat in the theater, and here's what makes active galaxies more than just cosmic fireworks. All that energy pouring out of the nucleus can heat up or blow away the surrounding gas that a galaxy needs to form new stars. This process, called AGN feedback, is thought to be one of the main reasons why so many massive galaxies today are basically dead. Remember those gas-poor ellipticals and lenticulars from earlier? AGN feedback is one of the leading suspects for why they ran out of fuel. A galaxy that looks quiet that invisible light might be screaming in X-rays, and that scream might be what killed its star formation. So active galaxies aren't just rare, flashy outliers. They might be the reason the universe's biggest galaxies stopped growing. Now, let's zoom out, way out, past individual galaxies entirely to the neighborhood we actually live in, the local group. So we've been talking about all these different types of galaxies like they exist in isolation. They don't. Galaxies live in neighborhoods, and ours has a name. The local group is a collection of roughly 80 plus galaxies spread across a volume about 10 million light years wide. That sounds like a lot of galaxies, but most of them are tiny dwarfs. The heavy hitters are really just two, the Milky Way and Andromeda. Everything else is basically orbiting one of them. The whole structure is organized into two gravitational lobes. Think of it like two big kids on a playground, each with their own entourage. One lobe is anchored by the Milky Way and its satellites, things like the Large and Small Magellanic Clouds, the Sagittarius Dwarf, and a bunch of ultra-faint systems we keep finding. The other lobe is anchored by Andromeda, also called M31, along with its own swarm of satellite galaxies and the Triangulum Galaxy hanging nearby. These two lobes are separated by about 2.5 million light years. Now here's where it gets personal. The total mass of the local group is estimated between 1.3 and 2.3 trillion solar masses, and Andromeda alone carries roughly 1.5 trillion of that. It's the gravitational heavyweight of our neighborhood. The Milky Way is not the main character here. We're the second biggest kid on the playground, and we're getting closer. The Milky Way and Andromeda are approaching each other at about 123 kilometers per second. The center of mass of the entire local group sits about 450 kiloparsecs from us, which means we're the ones doing most of the falling. This isn't speculation, it's measured. The merger is gravitationally inevitable, but don't panic. Inevitable on cosmic timescales means about 4 to 5 billion years from now. You will not be around. Neither will Earth's oceans, probably, but the collision will happen. The two spirals will distort, merge, and likely form a giant elliptical galaxy. Some astronomers have already named it Milkomeda, which is honestly terrible, but it's what we've got. Even now, the local group isn't sitting still. The Magellanic Clouds are on a complex orbit that may end in their own merger with the Milky Way. Satellite galaxies are being tidally shredded and absorbed. Our galactic neighborhood is a slow-motion collision that's been unfolding since the early universe, so that's home. Two big spirals, a few dozen dwarfs, and a future that ends in a merger. But the local group is just one tiny pocket of structure. Zoom out further and things get a lot bigger. Galaxy superclusters. So the local group has about 80 galaxies. That's our neighborhood. The Virgo supercluster, which our local group sits on the outskirts of, contains more than 47,000 galaxies. Let that sink in for a second. 47,000 galaxies, stretched across a major axis of roughly 147 million light years. The binding mass of this thing is approximately 1.48 quadrillion solar masses. Its total luminosity is about 3 trillion times that of our sun. The local group, with its roughly 2 trillion solar masses, is a rounding error. We are a suburb of a suburb, and the whole thing is moving. Galaxies out to roughly 50 megaparsecs, that's about 163 million light years, are streaming toward a region called the Great Attractor near the Norma cluster at around 600 kilometers per second. Not individual galaxies drifting, entire clusters, entire superclusters, being gravitationally dragged toward a mass concentration so enormous we can barely observe it because it sits behind the plane of our own Milky Way, which blocks our view. We are falling towards something we can't fully see at 600 kilometers per second, and there is nothing anyone can do about it. Fun fact, but here's where it gets philosophically strange. You'd think something called a supercluster would be, a thing, a coherent gravitationally bound structure, and the truth is it might not be. The boundary between a real bound supercluster and just an overdense region of the cosmic web, basically a slightly thicker strand in the universe's filament structure, is genuinely contested among astronomers. Many structures we call superclusters may not be gravitationally bound at all. They're just regions where galaxies happen to be a bit more crowded than average. The Virgo supercluster itself may not survive as a coherent structure on cosmological timescales. The universe's expansion is accelerating, driven by dark energy, and that acceleration is slowly pulling apart everything that gravity can't hold tightly enough. Galaxy clusters will probably stay bound, but the supercluster as a whole, it might just dissolve. The galaxies on its edges drifting away into an increasingly empty, increasingly cold cosmos. So this is where we end up. We started with spiral arms and star-forming regions. We built up through galaxy types, groups, clusters, and now we're at the largest coherent structures in the observable universe, structures so big that coherent might be too generous a word. Structures that contain tens of thousands of galaxies, span hundreds of millions of light years, and may not even hold together. The universe built all of this, and it might also be the thing that takes it apart. Still beautiful, still temporary, like everything else. If you enjoyed this video and want to see more, click the video on the screen now.